Hi guys, this is chapter 4, lesson 4-6, regression and median fit lines, and we are going to continue our conversation about scatter plots. And in the last lesson we were eyeballing lines, just drawing them through a scatter plot to see if we could kind of match the general trend of the scatter plot. And in this lesson we're going to use technology to do that. If you have a TI-83 or a TI-84, your calculator will do this for you, and at some point I can show you how to do that. But we're just going to use an online calculator, which is also acceptable. So when you're looking at a scatter plot, very often there's maybe a general trend. In this case, we could draw a line through the middle of these dots like we did in the last lesson and say that maybe there's a little bit of an upward trend. It doesn't match very well. It would match better if maybe the lines were closer, the dots were closer to the line or something like that. Sometimes we could see that the dots are definitely trending up. Sometimes we can see that the dots are definitely trending down, sometimes very close to perfect. Sometimes there's just no correlation whatsoever. The dots are just random. And sometimes you have to use a bit of the imagination, but you can see a trend. So if we see a perfect line going up, we will get something called a correlation coefficient. We call that R, and we will say that R is 1 if it is perfect. If it is a perfect line going up, this one right here is pretty close to a perfect line going up. If we have a perfect line going down, we will say that R equals -1. This one is pretty stinking close to perfect. And then if we have no correlation whatsoever, we will say that R is 0, and that's maybe like this one. This would be something negative, but not somewhere maybe not -1, but not 0 either, something in between 0 and -1. And this would be something between 0 and positive. So it's kind of like a range. So we have -1 is down there for downhill for perfects, and then 0 is nothing, and then 1 is here. I wrote this going backwards. That would be perfectly going up. So let's go to an online calculator. And I'm also looking at page 259 in your textbook and number 1, which says a local university is keeping track of the number of art students who use the pottery studio each day. So on day 1, there were 10 students, and on day 2 there were 15 students, and on day 3 there were 18, and day 4 there were 15, 5, 13, 6, 19, 7, 20. So it says write an equation of the regression line and find the correlation coefficient. So what I have done is I have typed in the x values on the first row, 1, 2, 3, 4, 5, 6, 7, and the y values on the second row. And I actually read the directions because all these are slightly different. And then I'm going to click submit data. And what I get is a scatter plot that you can see is truly pretty scattery, actually. And I'm not sure why there would be a linear trend between the days and the number of students who are using the pottery studio. So this is probably pretty random, but it almost does look like as the week goes on, perhaps more students use the pottery studio. Actually, I think more logically, there's the most on the 3rd day, and the 6th day and the 7th day. So I don't know, maybe there is a slight linear trend. So what this has done for us is they have actually written an equation for us where it says regression line equation. And here, I can probably do this so I can write on it a bit. Regression line equation, y equals 11 plus 1.17 lots of decimal x. And so we could maybe simplify that a little bit and say y equals 1.18 x plus 11. Interestingly enough, it thinks, on the graph it doesn't really look like it crosses at 11. It must be just an illusion of some kind. But notice that here is B. I've just rearranged it to be in a form we're more used to. Here's my slope. It calculated slope here for us. It calculated an intercept for us. Mean just means it averaged out the x's and it averaged out the y's. That's all cool. And our sample size was 7 data points. If we want a correlation coefficient, I have to go away from my screenshot. We can ask for that. And what we find out is that the correlation coefficient is 0.7, lots of decimal. And 0.7 is actually closer to 1, like an upward trend line, than it is to 0. So we would say that there probably is some kind of a trend here. It's not a strong one. So we would say this is a weak positive correlation. Let's pop over to the homework and look at those problems. So the table and scatter plots show the time spent texting and the time spent exercising by each of 9 students last week. And so in the table, you can see here the information that they've gathered. So a student that texted for 2 hours, exercised for 6.42 hours. A student that texted for 6 hours, exercised for 5.5, and all those other data points in between. And you can see that they have plotted them and they have drawn a line of best fit through there. The calculator just does the most amazing job of putting the very most average placed line in there. And then they ask us for some information, so I'm going to go back to the other screen here. So when they ask us for the observed time spent exercising, the observed just means what did we observe? So that's right in the table. So I'm going to say time spent texting in hours was 4, go down the table, and I can see that the time spent exercising was 4.50. Okay, at 6.0, it was 5.50. So hopefully you can see that. And now I'm going to calculate the predicted time. The line we have drawn through there is for the purpose of predicting things. So I'm going to pull up the calculator here, and I'm going to use my equation that you can see up there, y equals negative 0.4x plus 6.93. The calculator did that for us, and we are going to plug in 4 hours and see what it predicts. So I have negative 0.4 times 4 for our first problem, plus 6.93. 6.93 is our y-intercept, our starting amount. That would be how much we expect that the students are going to exercise if they don't text at all. Okay, so I'm going to hit enter. 5.33 is what I'm predicting based on my equation. Okay, so now we're going to calculate a residual. So a residual is just what is the difference between what we observed and what we predicted. So write this in your notes so that you have it when you get asked this question. To calculate the residual, we do the observed minus the predicted. So I'm going to go to my calculator and I'm going to take the observed, which is 4.5, minus the predicted, which is 5.33, and get negative 0.83. That's my residual. That's how much different my predicted was than my observed. My observed, the actual student actually exercised less than I was predicting. So let's go calculate the predicted time and exercise for a student that texts 6 hours. So we need to get the calculator, and we're going to go negative 0.4 times 6 hours. This time, that's our x, plus 6.93. Don't forget we're using the equation from above. And we hit enter, and we get 4.53.
That's what I'm saying.
Keep moving around that. And notice it's positive because, oh, wait. It's positive because that's what it is. I'm not calculating the residual yet. To calculate the residual, I'm going to go 5.5 minus 4.53. Observed minus predicted. And that gets me 0.97. It's positive. Now I'm to the point I started to say before. It's positive because my student actually exercised a little bit more than I predicted. So I'm going to hit check. In problem number 2, I have some scatter plots, and what I'm going to do is not only look at the line of best fit, but I'm going to take my residuals, those numbers I was just calculated where I do observed minus predicted, and I'm going to graph those. And if, when I graph them, they make a perfect line across the x-axis, then I know it was a perfect graph because the residuals were all 0, right? So if the residuals are all 0, they will be like residual plot 2 there. See how that's a perfect flat line? That perfect flat line must go with scatter plot B because scatter plot B is a perfect line. So I'm actually going to go down here and choose scatter plot B to go with that perfect residual. If I'm looking at scatter plot A, it's a pretty good model, but not perfect. So looking down between residual plot 1 and residual plot 3, I'm going to choose residual plot 3 because it's relatively going along the x-line, but not perfect, so it seems to match A. And then we can see that C is going to match residual plot 1. That is actually not... that is not really a line at all, is it? If you know anything about parabolas, that's close to a parabola. It is not linear. So that's just not even a good model. So let's go down here to the next question and say that that's not an appropriate model. Okay, for the second question, that's a perfect model. And for the third one, that is good, but not perfect. All right, in this one, we are looking for that R number. So if I look at figure 1, I would say that is close to 1, but not exactly. Figure 2, I would say that is somewhere not quite close to -1, but it's on the way to -1. Figure 3, that's getting pretty close to a perfect 1. And figure 4 looks totally random. Like, I don't think there's any correlation there at all. So number 1 says, for which data set is the correlation coefficient R the closest to -1? I would say that has to be figure 2 because none of the other ones, figure 1 and figure 3, are positive. Figure 2 is kind of close to -1 and figure 4 is nothing. So let's call this figure 2. And number 2 says which data set shows the least evidence of a linear relationship? Well, that's definitely 4. So random. And number 3 says for which data set does the correlation coefficient R appear to be equal to 1? That has to be figure 3 because they're very close to being in a line just the way they are. So that's how we reason through those. All right, go to Alex and work those 3 problems for yourself.